MEP errors don't fail early. They fail when everything is already installed. The biggest risks on your project are the ones you cannot see. They hide above the ceiling tiles. They are buried within concrete slabs. They are sealed behind drywall, mechanical, electrical, plumbing. These systems are the lifeblood of any modern building. Yet these complex networks are often the last to be fully verified. This creates a significant blind spot. We spend months coordinating models in pre-construction. We run countless clash detection reports, but we often fail to ask the most important question. Is what we designed actually what got built? And is it built correctly? The gap between the digital twin and physical reality is where catastrophic budget overruns and schedule delays are born, often surfacing when it's far too late to fix them cheaply. This hidden risk is not theoretical. It's a practical, everyday problem that costs the industry billions. A single duct installed a few inches off can have a cascading effect. It can obstruct sprinkler heads. It can interfere with lighting fixtures, or block access for future maintenance. These problems aren't typically discovered on a casual site walk. They're found during commissioning, when systems fail tests. They're found during final inspections, when an inspector flags a code violation. Or worse, they're found by the owner's facility team years later, causing warranty claims and reputational damage. The assumption that a clash-free model equals an error-free installation is dangerous. MEP installation is a high-stakes game of inches. A small deviation can have massive consequences. Imagine a chilled water pipe installed without the specified clearance from a high-voltage conduit. The model looked perfect. The clash report was clean. But on-site, a minor adjustment by an installer to avoid structure created a major safety and operational hazard that went unnoticed. This is not a failure of craft, it's a failure of process. We find theoretical problems digitally, but struggle to verify the physical work. It's time to close this gap and bring the same rigor to as-built validation as we do to pre-construction coordination. Pressure to move quickly leads to small, undocumented deviations. An installer might shift a conduit to make work easier, unknowingly creating problems for trades that follow. Without a rapid, reliable way to check installed work against the coordinated model, issues compound. They stack up behind walls and above ceilings, waiting to be discovered at maximum cost and disruption. Final weeks should be fine-tuning, not frantic, expensive rework. We must stop reacting and start proactively validating that what is built matches the plan in every critical dimension. We really need to change how we approach this. The very nature of MEP systems makes them a prime source of late-stage project pain. They are the first to be installed in many areas and the first to be covered up. Drywall, ceiling grids, architectural finishes quickly conceal the intricate web of pipes, ducts, conduits. This concealment is a double-edged sword. While it is necessary for the building's function and aesthetics, it means that installation errors are effectively sealed away, ticking like time bombs. A plumbing drain sloped incorrectly might not be discovered until fixtures are installed and tested, weeks or months after the pipe itself was encased in concrete or hidden behind a finished wall. The cost to fix that problem is now 10 times what it would have been if caught immediately. These expensive surprises almost always emerge during the most critical and high-pressure phases of a project. Commissioning is often the first time the complete MEP network is put through its paces. A duct too small to deliver required airflow. A valve inaccessible for servicing. These are not simple fixes. We have all become very good at clash detection. We use sophisticated software to coordinate our BIM models with incredible precision. We generate reports showing every instance where a pipe hits a duct. We generate reports showing every instance where a conduit intersects with a steel beam. We spend hundreds of hours in coordination meetings. Teams resolving these digital conflicts in coordination sessions. This process is valuable. It is essential. But it is not enough. A clash-free model is only a plan. It is a highly detailed, well-coordinated plan, but it is still just a plan. It does not and cannot guarantee that the work installed in the field will perfectly match that plan. Believing that clash detection is the same as quality validation is a fundamental misunderstanding of where risk truly lies. The purpose of clash detection is to resolve geometric conflicts between different systems within the model. It answers the question, do our designs fit together in the digital world? It is a pre-construction design tool. On the other hand, as-built validation answers a completely different and far more practical question. Did we build what we designed, and is it in the right place? This is a construction phase quality assurance process. The field is a messy, dynamic environment. Unforeseen site conditions, small improvisations by installers, and simple human error can all lead to deviations from the coordinated model. Your clash detection software has no idea that an installer decided to route a conduit run under a duct instead of over it to save a few minutes. When you cut through all the complexity, the vast majority of expensive MEP installation errors come down to two fundamental issues. These are not complex engineering problems. They are simple spatial problems. If we can consistently verify these two things, we can prevent an estimated 90% of the rework that plagues our projects. The two checks that matter are location clearance, visual. Two-panel diagram showing location left and clearance right. That is it. Everything else is secondary. By focusing our validation efforts on these two core principles, we can create a powerful, efficient, and highly effective quality assurance process that delivers real results. Forget about analyzing every single nut and bolt. Focus on what causes the biggest headaches and the most expensive fixes. First, let's look at location. Is the MEP element installed where the coordinated model says it should be? This is not just about XYZ coordinates. It is about its position relative to the building's structure and other systems. Is that run of electrical conduit in the correct stud cavity? Is that main plumbing stack located in the designated shaft? Is the air handling unit placed on its pad with the correct orientation? A deviation of just a few inches in the location of a primary duct or pipe run can cause a chain reaction of problems for every trade that follows. Verifying location early and often ensures the backbone of your MEP system is installed according to the coordinated plan. The second core check is clearance. Is there enough space around the MEP element to function correctly? Be serviced meet code? This goes beyond simple clash detection. A pipe and a conduit might not be clashing in the model, but are they installed with the required 1-inch separation? Is there the mandated 3-foot clearance in front of that electrical panel for service access? Does that sprinkler head have the necessary unobstructed spray pattern? Clearance issues are a major source of failed inspections and long-term operational headaches for the building owner. Validating clearance ensures safety code compliance, long-term serviceability of the building you are turning over. By focusing on just these two checks, location and clearance, we can simplify the entire validation process. We do not need to get lost in the weeds. We need a fast, reliable way to confirm major components are in the right place and have the right amount of space around them. This targeted approach lets us filter out the noise and focus on deviations that cause cost and schedule impacts. It transforms quality control from a subjective, manual process into a data-driven, systematic one. These two checks are the foundation of a modern, reality-based MEP validation strategy. So yeah, keep it simple and check those two things. Moving from theory to practice requires a simple, repeatable workflow. The good news is, modern tech makes reality-based validation faster and more accessible. You do not need to be a laser scanning expert or a data scientist. The process can be broken into 4 straightforward steps: capture, point cloud, align, automated checks. This workflow is fast, efficient, and integrates into your existing project schedule. The goal is to capture reality, compare it against the plan, and get actionable answers in hours, not weeks. It's about making data work for you on the job site. The first step is capture. This involves using a laser scanner to capture the as-built conditions of your MEP installation. Modern scanners are fast, portable, and easy to use. A single operator can capture a massive area, like a 20,000 square foot floor plate with exposed MEP, in just a few hours. The scanner creates a dense, measurable 3-dimensional point cloud, which is a digital copy of the physical space, accurate to within millimeters. This capture should be done at key milestones, such as after the overhead MEP rough-in is complete, but before the ceiling grid goes up, or before drywall goes up. This timing is critical for catching issues before they are concealed. Step 2 is processing the raw scan data into a usable point cloud. This used to be a specialized, time-consuming task, but modern software platforms have largely automated it. You simply upload the raw data from the scanner to the cloud. The software automatically stitches the multiple scans together, cleans up any noise or erroneous data points, and produces a clean, unified point cloud. This digital replica of your job site is the foundation for your validation checks. The entire process, from uploading data to having a ready-to-use point cloud, can now take a matter of hours, allowing for near real-time analysis of site conditions. The third step is to align the point cloud with the BIM coordination model. This is the crucial step where the as-built reality meets the as-designed plan. Again, modern validation software automates this alignment. The platform intelligently recognizes common geometry, like columns and slabs in both the model and the point cloud, and perfectly overlays them. Now you have a direct one-to-one comparison. You can visually see where a real-world pipe deviates from its modeled location. This aligned data set is the raw material for your analysis, providing a clear and unambiguous picture of any and all deviations between the design intent and the installed reality. The final step is to run automated checks. This is where the magic happens. Instead of spending days manually inspecting the aligned model and point cloud, you use software to automatically analyze the data for you. You can set specific tolerances for the two key checks, location and clearance. For example, you can instruct the software to flag any pipe that is more than 1 inch away from its designed location. Or you can tell it to highlight any area where the code-required clearance around an electrical panel has been violated. The software crunches through millions of data points. A raw point cloud aligned with a BIM model is just a massive collection of data. On its own, it is overwhelming and not very useful. You could spend days panning and zooming, visually looking for problems. This is not an efficient use of anyone's time. The real power comes from using automation to filter this sea of data and turn it into actionable intelligence. The goal is not to find every millimeter of deviation. The goal is to find the deviations that matter. Real project risk. Automation systematically and objectively finds these critical issues. The first way automation helps is tolerance filtering. Before analysis, define what correct means for your project. Set a tolerance, e.g., 1 inch. Show software ignoring small deviations and flagging breaches. Anything outside that 1 inch tolerance needs review. Automation filters out the noise and reduces thousands of tiny discrepancies to a concise list. This lets your team focus where it's needed most. Next, element-level validation. The platform understands individual BIM elements, not just point clouds. It knows one object is a 12-inch round duct. It knows another is a 4-inch steel pipe. It knows another is a 480-volt electrical panel. It checks the as-built points against each specific design element. That enables highly specific, relevant checks. Example, clearance check for electrical panels. Ensure 36-inch service clearance. Apply a different clearance rule to VAB boxes. This detail is impractical with manual inspection. Finally, actionable alerts. The output isn't a 300-page unreadable PDF. It's a simple, visual, immediately understandable summary. Deviation heat maps show where model and reality differ most. The system isolates out-of-tolerance elements and lists them. Alerts can be tagged, assigned to the responsible contractor, and tracked to resolution. This creates a closed loop for identifying, communicating, and resolving installation errors before they get covered up. Think about the traditional way we handle on-site coordination issues. A problem is discovered by a superintendent or a foreman. They make a phone call. An RFI is written. A meeting is scheduled with the project manager, the designer, the affected subcontractors. Everyone gathers in the trailer to look at the drawings, argue about what went wrong, and debate how to fix it. This process can take days, sometimes weeks. While everyone is stuck in meetings, work in that area of the project grinds to a halt. This is the detect and react model, inefficient and expensive. It burns valuable project hours and kills momentum. Now contrast that with a reality-based validation workflow. The laser scan is completed on Monday morning. By Monday afternoon, the data is processed, aligned, and the automated analysis is complete. The VDC manager receives a notification with a concise report of 5 critical installation errors. One is a primary duct run that is 6 inches too low, creating a future conflict with fire sprinkler piping. The report includes a heat map, a 3-dimensional view of the deviation, and the exact location on the floor plan. There is no ambiguity. There is no argument about what the condition is. The data provides objective, indisputable proof of the problem. Instead of scheduling a fire drill meeting, the VDC manager can immediately share this visual evidence with the mechanical contractor. The report can be viewed on a tablet right at the point of installation. The conversation is no longer about if there is a problem, but about the fastest way to solve it. The mechanical contractor can see the issue clearly and understand its impact on the upcoming sprinkler installation. They can develop a plan to correct the duct elevation immediately, before the sprinkler team even mobilizes to that area. What previously took a week of meetings and RFIs is now identified and resolved in less than a day. This shift from long, subjective meetings to fast, data-driven decisions is transformative. It frees up your project managers, superintendents, and trade partners to focus on building, not on arguing. It replaces opinions with facts. The point cloud does not lie. When everyone is working from the same objective source of truth, collaboration improves dramatically. Disputes are reduced because the data clearly shows what was installed versus what was planned. This data-driven approach allows you to manage by exception, focusing your team's valuable time and energy on solving the handful of real problems that the automated analysis has identified rather than manually hunting for them. Adopting a reality-based validation process for MEP, it is not just about creating a better BIM model or a fancy report. It is about delivering tangible, bottom-line benefits to your project. The most immediate and obvious benefit is the dramatic reduction in rework. By catching installation errors in hours instead of weeks or months, you are fixing them at the point of lowest cost. Adjusting a hanger for a duct run before the ceiling is installed might cost a few $100s in labor. Tearing out a finished hard-lid ceiling to make that same adjustment after a failed inspection can cost tens of thousands of dollars and delay the project by a week. These savings go directly to your bottom line. This proactive error detection has a powerful effect on your project schedule. Rework is a schedule killer. It not only takes time to perform the fix itself, but it also creates a cascading effect of delays for all the trades that follow. By validating installations at key milestones, you ensure that the work is correct before it is covered up, allowing subsequent trades to proceed with confidence and without interruption. This leads to a smoother, more predictable workflow. It helps you hit your critical path, milestones more reliably. Ultimately, it allows you to finish the project faster, avoid liquidated damages, move on to your next profitable job sooner. The benefits extend all the way to project closeout and handover. Commissioning becomes a much smoother process because you have been systematically verifying the installation all along. There are far fewer surprises when systems are tested for the first time. Final inspections with the authority having jurisdiction are more likely to pass on the first attempt, because you have already checked for common code violations related to location and clearance. This results in a faster, less stressful closeout phase. It allows you to get your final payment and retention released without a long, drawn-out punch list of MEP fixes. Finally, you are turning over a better building to your client. The as-built documentation you provide is not just a set of red-line drawings. It is a highly accurate digital record of the installed systems. This data is incredibly valuable to the owner's facility management team for future maintenance and operations. Delivering this level of quality and documentation strengthens your relationship with the client. It builds trust and enhances your reputation as a forward-thinking, quality-focused contractor. This reputation is your most valuable asset, leading to repeat business and a stronger position in the marketplace. The investment in reality validation pays for itself many times over, not just on one project, but across your entire portfolio. If you're only checking clashes, you're missing reality. Validate what's actually built. MEP systems are hidden. That's why errors are so expensive. Most teams think coordination means control. It doesn't. First, is the system where it should be? Second, does it have the required clearance? Capture site reality. Generate point cloud. Align with BIM. Run automated checks. The earlier you detect MEP issues, the cheaper they are to fix.